Hello, I am excited to introduce our work Fast-StrucTexT in IJCAI 2023. In this paper, we propose an efficient Hourglass transformer by performing model-guided dynamic token merging to reduce the number of tokens. In addition, we develop a dual multimodal interaction mechanism named symmetry cross-attention, which can enhance the multimodal feature fusion from visual documents and provide modality-guided information. In this figure, we visualize the attention maps and token interactions of a standard transformer in the inference phase. In particular, Figure A displays the aggregated attention map of all transformer layers. The left half shows a self-attention map inside words and the right half shows the cross-attention map between words and segments. We resample two regions with highlighted red boxes and zoomed in Figure B. Moreover, for closer observation, Figure C gives the correlation visualization curves and lines of words and segments based on attention scores related to Figure B. Almost the words and segments belonging to one semantic entity have significant correlations to their counterparts, indicating a high redundancy between irrelevant tokens in attention scores, which illustrates two key viewpoints. 1. Strong correlations are existed across granularities. 2. There is rich redundancy in attention computation for document. Fast-StrucTexT consists of three parts: Hourglass encoder, merging and extension blocks, and symmetry cross-attention. As shown in figure, we design an Hourglass transformer that consists of merging and extension blocks, which receives the full-length sequence as input and compresses the redundant tokens progressively. Cross-attention has shown the effectiveness of multimodal learning on the vision and language tasks. To enhance the interactions among textual and visual modalities, we introduce symmetry cross-attention SCA module to model the cross-modality relationships, which consists of two dual cross-attentions to handle the text and visual features in this work. We also leverage SCA to provide cross-modality guidance for token merging in the merge blocks. The SCA is defined the formula as follows. The M block suggests merging nearby K tokens with weighted 1D average pooling, where K is the shortening factor. In view of the multimodal hidden states, A referred weighting is predicted from another modality by a linear layer. The process is denoted in the right figure. The E block is required to transform shortened sequence of hidden states back to the entire token level state. In detail, we simply apply repeat upsampling method to duplicate the vector of each merged token for K times. This method is computationally efficient. For maintaining the distinct information of tokens, we fed the hidden states from the corresponding M block into the E block through a skip connection. We adopt four self-supervised tasks simultaneously during the pre-training stage. MVLM masks some tokens from the language sequence and then the model is required to reconstruct the corresponding tokens. SOP uses two normal order adjacent sentences as positive examples and others as negative examples. SOP aims to learn fine-grained distinctions about discourse-level coherence properties. GTR constructs a ground truth matrix with 0 to 9 to express the spatial relationship between each pairwise text segments. In the TIA task, some image patches are randomly masked with 0 pixel values and then the model is pre-trained to identify the masked image patches according to the corresponding textual information. We conclude with evaluations of Fast-StrucTexT on 4 benchmarks, as well as ablation studies. All the length of input tokens is 640, while 512 text tokens and 128 image tokens. We use Paddle 2.3.2 deep learning framework. We do pre-training on 8 NVIDIA Tesla 100 GPU and do inferencing on NVIDIA GTX 2080 Ti GPU. The entity labeling task aims to assign each identified entity a semantic label from a set of predefined categories. We perform an arithmetic average on the text tokens which belong to the same entity field and get the segment-level features of the text part. To yield richer semantic representations of entities containing the multimodal information, we fuse the textual and visual features by the Hadamard product operation to get the final context features. Finally, a fully connected layer with softmax is built above the fused features to predict the category for each entity field. The comparison results are exhibited in this table. Our Fast-StrucTexT achieves state-of-the-art FPS and outperforms the performance of the current state-of-the-art model by 156%. Fast-StrucTexT achieves a 1.9 times throughput gain and comparable F1 score on the CORD and SROAE entity labeling tasks. To demonstrate the effectiveness of Fast-StrucTexT in Chinese, we pre-train the model in a self-built dataset which consists of 8 million document images in Chinese, and fine-tune the pre-trained model on IJCAI. This table illustrates the overall performance of the IJCAI dataset, where our model obtains the best result with 98.18% F1 score. The entity linking task desires to extract the relation between any two semantic entities. We use the bi-affine attention for linking prediction, which calculates a score for each relation decision. In particular, for entity, two MLPs are used to project their corresponding features, respectively. After that, a bilinear layer is utilized for the relation score. We compare Fast-StrucTexT with several state-of-the-art methods on FUNSD for entity linking. Our method achieves a comparable performance. We replaced a variety of popular lightweight backbones for evaluation. As shown in this table, Fast-StrucTexT can achieve the highest performance and FPS. The point here is that Transformer takes responsibility for token feature representation, which could benefit from large model size. It is the reason why those lightweight architectures lead to worse performance. This table gives the results of different merging strategies for entity labeling tasks on FUNSD. The experimental results show the effectiveness of our token merging method. We study the hyperparameter K. We have evaluated multiple benchmarks and have established that the setting K equals 2 is the best trade-off for document understanding. In addition, we can adjust the K in the fine-tuning stage. Nevertheless, ensuring consistency of K during pre-training and fine-tuning can take full advantage of knowledge from pre-trained data. Our framework supports multi-scale pre-training with a list of K factors to handle different shortening tasks. Our token merging can adapt to the arbitrary length of the input. The ratio of merging is adjustable and determined by the value of K and the number of M blocks and E blocks. Referring to this table, we investigate the ability of our method with various sequence lengths. The experimental results show that the speed and computation gains become more pronounced with the sequence length increasing. Thanks for your attention.